Today we are discussing Bellman Ford algorithm to find the shortest path from a source node to all the other nodes in the graph. We have already discussed Dijkstra's algorithm for the same exact purpose. If you haven't watched my video on Dijkstra's, please take a few minutes to watch it, because in that I've discussed why Dijkstra's algorithm doesn't work on graphs with negative weights. As a quick recap, if I apply Dijkstra's on this current graph starting from source node A, there are two neighbors to node A, which are node D and node B. We add both of them to the priority queue. Since node D is the closest to node A at distance 2, we pop it from the priority queue and mark it as visited. And then we add its neighbor to the priority queue. Once we have marked this node D as visited, we would never come back to this node D again. So the shortest distance from source node A to node D will be 2. But there is another path from A to B via B and C whose total cost is 3 plus 2 minus 4 equal to 1. Dijkstra's algorithm never explores this path because it assumes that all the edges have positive weight. Hence, once it visits nodes that are closer to the source node, it marks them as visited even if there is another path back to the same node again, because as we add more edges to the path, the total cost of the path keeps increasing because it assumes that all the edges have positive weight. That's why Dijkstra's algorithm doesn't work for graphs with negative edges. That's why we apply Bellman Ford algorithm for graphs with negative edges. But a limitation of Bellman Ford algorithm is it works on graphs with negative edges, but it does not work on graphs with negative cycles. To understand what exactly are negative cycles, let me redraw this graph. I have rewritten the same graph here so that it's easier to understand cycles. If you notice, there is a cycle formed here. And weight of this cycle is weight of the edge B to C, which is 2, plus C to D is minus 4, and D to B is plus 3. So the weight of the cycle is 1. Let's say if this edge was minus 7 instead of minus 4, then the weight of the cycle would be 2 plus minus 7 plus 3, which is equal to minus 2. Which means every time we run through this cycle, the cost is minus 2. That means the shortest path from source node A to node E would be, first we go from A to D, and then repeat in this cycle infinite times, and then take the last step D to E. So the shortest path from A to E would be 2 plus, we repeat the cycle infinite times, so the cost would be minus 2 multiplied by infinite plus cost of the edge D to E. So the total cost would be minus infinite. So in case of a graph with negative cycle, no algorithm is guaranteed to find shortest path. That's the limitation of Bellman Ford algorithm. Let's go back to the original graph and understand the theory behind Bellman Ford algorithm. To understand Bellman Ford algorithm, there are a couple of claims we make. The first one is all the shortest paths we find from Bellman Ford algorithm will be simple paths. That means these paths will not have any repeated edges. Repeated edges indicate there is a cycle in the path. But we already discussed none of the algorithms work for cycle with negative weights. So we only work with cycles with positive weight. If the cycle weight is positive, then the cycle is going to only increase the total cost of the path, and there's no point in taking this cycle. Hence, it proves that all the paths we take are going to be simple paths. And the second claim is maximum number of edges in the shortest path will be number of nodes minus 1. Because claim 1 already states that all the shortest paths are simple paths, that means there are no repeated edges or repeated vertices. So if we don't repeat any vertices, there are at most n vertices. So in a given graph, a shortest path can have at most n nodes. If the path goes through all the n nodes, that means there are n minus 1 edges, like in this case. This path from A to E goes through all the nodes B, C, D. So the number of edges in this path will be total number of nodes, which is 5 minus 1 equal to 4 edges. With these two claims, let's see how Bellman Ford algorithm works. So here is the pseudocode for the Bellman Ford algorithm. We start off by setting distances to all the nodes as infinite. Then we set the distance to source node as 0, and we repeat this number of nodes minus 1 times. Why the number of nodes minus 1 times? It's because, as we discussed previously in one of the claims, that there could be simple paths in the graph that has at most number of nodes minus 1 edges. So to explore all those paths, we repeat this for number of nodes minus 1 times. In each iteration, we run this relaxation, where in each iteration we go through all the edges uv and compare the distance to node v to distance to node u plus cost of the edge uv. If we found a newer path whose total cost is less than the cost of the previous paths, we update the distance to node v with the newer cost that is lesser than the cost of the path we found before. Let's try to work through this example graph and apply this algorithm. We start off by setting distances to all the nodes as infinite and distance to source node A as 0. Next, we run the first iteration of this. Let's go through all the edges and run the relaxation. We start with edge A to B, and we check distance to B is infinite, which is greater than distance to node A, which is 0, plus cost of the edge A to B, which is 3. So we update the distance to B to 3. Next, we check the edge AD. So distance to D is infinite, and distance to A is 0, plus cost of the edge is 2. So we update the distance to 2. Next, we consider this edge, where distance to node B is 3, and distance to node D is 2, plus cost of the edge is 3. We already have found a path to B that has the lower weight, so we don't update this distance. Next, we check this edge B to C. So the distance to C is infinite. We update the distance to 5, which is 3 plus 2. Next, we check this edge CD, and distance to node C is 5, and cost of the edge is minus 4. So 5 minus 4 is 1. So we found a newer path whose cost is less. So we update the distance to 1. Finally, we check this edge D to E. Distance to node E is infinite, which is greater than distance to node D, which is 1, plus cost of the edge is 2. So we update the distance to 3. That completes the first iteration, and we repeat this for another 3 times. So we start the second iteration with this edge. Distance to node B is 3, which is already less than or equal to distance to node 0 is 0 plus 3. So we don't update the distance here. Next, we consider edge AD. So distance to D is 1, which is already less than the distance to node A is 0 plus 2. So we don't update the distance to node D. Next, we check this edge. Distance to node B is less than distance to node D is 1, plus cost of the edge is 3. 3 is less than 4. We don't update the distance. Next, we consider this edge. 3 plus 2 is less than or equal to distance to node C, which is 5. So we don't update the distance. Next, we consider this edge. Distance doesn't change. Next, we run this edge. Distance doesn't change. We can continue this for another 2 iterations, but as we noticed already, in the second iteration itself, the distances to any of the nodes did not change. That means the distances are not going to change for any further iterations. So that's the Bellman Ford algorithm. The shortest path from A to B is this. Shortest path from A to C is this. Shortest path from A to D is this. And shortest path from A to E is this. And these are the shortest distances. So the runtime complexity of this algorithm is big O of, we repeat this for number of nodes minus 1 times, so it's number of nodes minus 1 times the number of edges, because we explore all the edges in each iteration. If we call this number of nodes as V, then the runtime would be big O of V minus 1 times E, which is same as big O of VE. As we discussed before, Bellman Ford algorithm does not work on graphs with negative cycles, but it can detect if the graph has negative cycle or not. The way it does that is, if we repeat this one more time and distances to any of the nodes change, that means there is a repeated edge which represents a cycle, and the distance is changed because this cycle is a negative cycle. If you found the video to be helpful, please support by liking the video and subscribing to the channel. I will see you in the next video. Thank you.